Okay, this is just going to be a quick review of all of the transformations and then a little bit of review from 7th grade about symmetry. I'm going to go through this rather quickly because if you did your whole transformation project by yourself, then this is all stuff you're familiar with. I just want to go over it one more time. So, reflections, there are 4 possible ones. So, the most common are across the x-axis. So when you reflect a point across the x-axis, the x stays exactly the same and the y changes sign. So if it was positive, it's negative. If it was negative, now it's positive. It just switches signs. Across the y-axis is exactly backwards. The y-coordinate is going to stay the same. You're not moving up or down. You're just switching from the left to the right. So the x-coordinate is the one that changes the sign. So always remember it's opposite of where you're reflecting. You reflect across the x-axis, the y changes signs. Across the y-axis, the x changes signs. Okay, the 2 probably new ones for geometry that you didn't study in the previous years have been across the line y equals x. Y equals x is an exact diagonal line going through the origin with a slope of 1. So it cuts diagonally through the coordinate plane. And what happens here is these switch coordinates. X and y switch places. So if this coordinate right here is 2, 3, then this one on the other side is 3, 2. No changing signs, no anything like that. They just exactly swap. Now, some of you, when you did your project, you said, oh, I put my coordinate, I put my shape over here, and I didn't want to reflect it on top of itself. So I told you could do y equals negative x, and this is one, so this is a little bit new for today if you didn't do that on your project. Here's the line y equals negative x, still going through the origin, but now it has a slope of negative 1, so it just cuts through the other way. It's still the coordinate when you switch them, they still swap places, x becomes y and y becomes x, but because of the negative slope, now they change signs. So let's say this coordinate over here was 1, 7. When it switches over here, now it's in quadrant 3, so it's negative 7, negative 1. They swapped places and they became negative. Okay, so here's just a quick practice. Why don't you pause right here and see if you can do all of these. So we're going to take the point negative 5, 2, and we're going to do it for all of these. So across the x-axis, the x stays the same and the y changes signs. Across the y-axis, the y stays the same and the x changes signs. Across y equals x, they just switch places. Across y equals negative x, they switch places and they change signs. Now these 2 down here are just across any vertical or horizontal line, and what's best for these is if you just draw a picture and you do the traditional reflections that you're used to. So x equals 3 is of course a vertical line right there, negative 2, 5. So across a vertical line, just like across the y-axis, the y is not going to change, the y is not going to change places. It's going to end up exactly the same. The x's, you just have to count. So from negative 2 to 3 is 5 places to get across the line right there, because I have to go negative 2, negative 1, 0, 1, 2, 3. So 5 places. So if I go 5 places on the other side from x equals 3, now I'm at 8. And so then you can count and make sure that you're symmetric. Same story with y is equal to 2. I should have put my graphs in the other place. So here's y equals 2. It is a horizontal line crossing over at 2. So we have the point negative 2, 5. So the negative 2 is going to stay there. It's just going to be, still going to be negative 2 on the other side. Let's see about the y coordinate. So from 5 to 2 would be 3 places. So if I go 3 places again to keep it even, now I'm at negative 1. Have mercy. Okay. Alright, rotations. So quickly you can do 90 degrees, and this one is going counterclockwise. So what happens when I go 90 degrees counterclockwise? They switch places, so x becomes y and y becomes x, and the y changes signs. Okay, you're going counterclockwise, you're going backwards. So the back sign is the one that changes, the one that used to be y. Going 180, nobody changes places, everybody just gets a negative sign. So negative x, negative y. Going clockwise 90 degrees is exactly very similar to going counterclockwise. Everybody still switches places, so x becomes y and y becomes x, but this time, instead of the y becoming negative, it's the x that becomes negative. Okay, so since it's going clockwise, it's going forward, then the front coordinate, the x, is the one that changes signs. And now one thing about these is, as long as you're going multiples of 90, you can still use these rules. So for instance, if I told you to rotate 540 degrees, well, 540 degrees, you're going 360, you're going all the way around. So that whole rotation doesn't count, because after 360 degrees, you just end up right back exactly where you were. Like for instance, if I took this point, if I went 360 degrees, I'd be right back where I was, so nothing happened. Take out the 360, I still have 180 degrees left. So I just pretend like I just am doing the problem with 180. I don't have to worry about the extra 360 degrees. Okay, pause right here and practice these to see if you're ready to go. Okay, so 90 degrees clockwise, I'm going to switch their places. That's what I'd always do first, and then I decide whose sign changes. So clockwise, the original x would have changed, so that's the 1. Same story for counterclockwise. The first thing I do is switch the places. Counterclockwise is backwards, so that would have been the y getting a sign change. 180, nobody switches, just everybody gets a different sign. Okay, 270 counterclockwise. So let's think about this. 270 counterclockwise, I could go 90, 90, and 90 again. Okay, so that would be 270. If I go 90, 90, and then 90 again, that would be 270. But that would be 3 transformations I would have to do. That would be a lot of work. I could also go 180 and then 90. That's better because that's only 2 transformations. But the easiest thing to do is, instead of going 270 counterclockwise, I can just go 90 clockwise. Any of these methods that I would have taken would have gotten me the same result. I just want to choose whatever less work. So I'm just going to pretend they said to go 90 clockwise, which I already did over here. So that is just negative y x. Oh, I'm sorry, y negative x. So there I am right there. 540 we already discussed over here. You just take out the 360 and you're left with 180. So then for 180, everybody stays in place but gets a new sign. Okay. Now this part was not on your transformation project, but you did it in middle school. I just want to review it with you very quickly. A figure has a line of symmetry if it can be reflected across the line so that the image coincides with the pre-image. Now that sounds scary, but it just means where can I fold it to where it will be in half. So like a heart, well, if I drew it good, would have one line of symmetry because I could fold it down the middle and it would be equal. Okay, a square would have 4 lines of symmetry because I could fold it here, 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 or here. So 4 lines of symmetry. You already know that. The line of symmetry, sometimes called the axis of symmetry, is the line in which you're dividing it on. Now this might be a little different, but it's the same concept. A rotational symmetry just means can you rotate it and it look the same. Instead of reflecting it or folding it, now can I rotate it and it look the same. The angle of rotation is the smallest angle through which a figure can be rotated. So what's the very tiniest I have to turn this and it looks exactly the same? And how many times I can do that until I get back to the exact right image through 360 degrees is called the order. So this sounds scary, but it's really not. So let's think about a square. If I take this square and I turn it, If I turn it 90 degrees, I have another square. If I turn it 90 degrees, I have another square. 90 degrees, I'm back to square. And then 90 degrees one more time, I'm back to the original shape that I was. So the angle of rotation is 90 degrees. The order is 4 because it took me 4 times to get there. So this is super easy because the order and the angle, when you multiply them together, always have to get you back to 360. So if I just figured out, hey, I have to rotate this 90 degrees, then I could just easily say, okay, 360 divided by 90, the order has to be 4. Or if you like it better that you can look at this and you can say, hey, I just have to rotate that 4 times. Then you can say, hey, the order's 4, so the angle must be 90. It's not as much work as it first seems. And we'll practice this in class tomorrow. You can do the exact same thing if you have a 3D object. It's just called plane symmetry instead of lines of symmetry because it takes a plane to slice it in half. And on this one, you don't have to tell how many lines, you just have to say yes or no. Can I cut it in half or can I not? So for this rectangular prism right here, yes, I can cut it in half. I can cut it in half this way as the picture shows. I could also cut it in half this way. So, and that doesn't matter. All you have to say is, yes, I can. Same story, instead of rotational symmetry, we call it symmetry about an axis. And all you have to say is yes or no. Can I turn this object any direction I want to? I can rotate it horizontally. I can rotate it vertically. Anywhere I want to. Can I rotate it and it looks the same? So for a cylinder, absolutely. I can rotate this 1 degree or 320 degrees or 450 degrees. It doesn't matter. I can rotate this all the time and it's going to look exactly the same. So yes, this has symmetry about an axis. And we'll practice those tomorrow.